Hello everyone. My name is Ade. I'll be the host. I want to welcome you all to our very first webinar, where our Chief Commercial Officer, Neal, will talk us through Purotech versus Granular Activated Carbon. Just a few housekeeping tips before we start. The session will be recorded and we'll share a copy of this recording at the end. Please feel free to submit your questions in the Q&A chat box and we'll try to go through all of them at the end. And this session should last about 40 minutes, included time for a Q&A. So hope you enjoy the session and I'll just hand it over to Neal.
Right. Thank you very much, Addie. Good morning, good afternoon, and I think good evening to some, since I got some emails from the folks in Australia and New Zealand. So we'll be talking a little bit about today about the Purotech G400 in comparison to granular activated carbon. I think I know a lot of you that are signing in, but for those of you who don't know me, I'm Neal Megonnell. I'm the Chief Commercial Officer for Puraffinity. I've been in the business for about 35 years, with roughly half that time in R&D. My background's in chemistry from the University of Pittsburgh and master's degree in chemical engineering in colloids, polymers, and surfaces from Carnegie Mellon, a degree that I never thought I'd use until PFAS came along. So it's actually a nice little fit. For those of you, again, that know me, you know some of the committees I'm on. I'm actually the chairman of the American Waterworks Association Activated Carbon Committee, and I'm the task group chair of the Activated Carbon Group under the Joint Drinking Water Treatment Units under NSF, as well as members of various other committees. So we'll get right into what we're going to talk about today. And at the end, questions and answers, feel free to ask as much as you want. I'm more than happy to answer. So we'll talk about the product itself, some of the physical properties of it, some laboratory testing. Obviously, this product is relatively new to the market. So it's different than some of the other materials that are out there. So some of the testing requirements and test methods that are being used, we'll talk about a little bit. Then we'll talk about some of the design parameters. Again, it's a different product, so it's not what I'd call a me too compared to activated carbon or ion exchange resins. We have a good bit of pilot data that we can share, which has actually led to a full-scale installation. So we'll talk about that, and then just some general conclusions at the end. So Purotech G400, what is it? Well, it's a granular media. It's about a 0.5 millimeter diameter. For those of you more familiar with mesh size, roughly a 20 by 50 mesh size. It's an alumina substrate with a patented surface coating, and this surface coating was developed specifically to capture PFAS compounds. So unlike some of the other media out there being used for PFAS, this material is targeted for PFAS with a patented technology. The bulk density is about a little over 50 pounds per cubic foot. So again, this is important when you're talking about how much material to put into a vessel. It's also important to talk about one other aspect of the material, which makes it interesting, and that this material is backwashable. So you can actually backwash it, for instance, to remove solids. If there's iron and manganese fouling, anything like that, the material can be backwashed. And due to the bulk density of the material, you can actually backwash the solids off and not move the media itself, not disrupting the mass transfer zone. We'll talk about mass transfer zones here in a little bit, for those of you that are not necessarily familiar with what a mass transfer zone is and why it's important. So laboratory testing. This goes back several years, actually, before my Puraffinity days. Several years back, the only thing anybody ever heard about was PFOA and PFOS. PFOA was obviously for the Teflon making process. PFOS was for the Scotchgard type materials. Initial theories really over-predicted the performance of activated carbon in particular. What we didn't understand at the time was the absorption kinetics. They just were not well understood. And part of the reason why is there's just not a lot of data on these compounds. If you go into a CRC or even online and try to find data on a lot of these compounds, it's very limited. So a lot of the work that was being done at the time, you need to have different physical properties, which for these compounds, again, you can't find much on. You can find a lot of data on, for instance, PFOA, PFOS, but not necessarily some of the other compounds. I think at last checked, the number of PFAS compounds that is by the US is a little over 14,000, and I think the Europeans are significantly higher in terms of the number they consider PFAS compounds. But things that are missing that are very important to determine how well something's going to absorb or be removed by various media, the solubility of the compound, refractive index, the vapor pressure, and the density of the compound. And again, these are not necessarily available for a lot of these. I've done a lot of work over the past years in trying to generate a good bit of information on how well a material is going to work for these compounds using something called SMILES notation, as well as the chemical structures of the compounds to basically predict some of the isotherms. The problem with some of these compounds, such as PFOA, is if you buy PFOA, it's not 100% linear compound. It's about 90% linear and about 7% branched. These compounds, the branched will have a different capacity than the linear compounds, so the kinetics and capacities will differ. One of the biggest challenges and what a lot of people like to do with any new media is run an absorption isotherm. It's a simple laboratory test. Basically, take a batch of water at various concentrations of the media, whether it be carbon, ion exchange resin, any of these other media, to the water. Let it stir for a period of time, and then analyze the water. The biggest challenge you have here is again, these compounds don't act the same as some other compounds, and the concentrations we're talking about are significantly less. If you look at for a drinking water standpoint, we're talking about part per trillion levels. It's very difficult to analyze down at those levels. And also the way the absorption isotherm test is run itself, the amount of material added per volume of water is very, very low. So it's very, very tough to control. So the data gets a little bit scattered. There's very limited data throughout the market for these compounds with various materials. And the data has limited value, as we'll see here in a little bit. One of the other tests that's run quite often is called the rapid small scale column test. This test was actually developed for granular activated carbon. Again, there's limited data out in the marketplace. There's RSSCT data, but it doesn't necessarily compare with full scale or pilot data. There's two assumptions that need to be made when you run the test. It's either constant or proportional diffusivity. I've seen data that's assumed both, and the numbers you get can be very different. So there's limited data in terms of scaling the RSSCT to an actual full scale or pilot data. It's something that needs to be developed, and is something that the industry is currently working on. It has not necessarily been verified for non-carbon media. So when you get away from the test method being developed for activated carbon being used for ion exchange resin or some of these other novel media, there's extremely limited data as to how well this scales up. And the PureTech G400 is a perfect example. Again, I mentioned it's a surface coated material. Part of the test method for the RSSCT is to break the particles down into smaller particles, which should represent the larger particle. Since it's a surface coated material, that's not necessarily the case. So the RSSCT is not necessarily a good test method for the PureTech G400. And one of the biggest issues with the RSSCT is just large variations in water quality. If you have a variation in your water quality, it's going to cause some issues with this test. So as you can see, there's a bunch of limitations that we have for the material, which leads to long testing times. So again, turn the clock back several years ago. First thing that people looked at again was absorption capacity. And running an absorption isotherm for PFOA, since that was really one of the first compounds people were looking at. The absorption isotherms were actually showing a coconut shell carbon was outperforming the bituminous coal-based carbons. The bituminous coal-based carbons were outperforming the lignite carbons. Unfortunately, what this test method doesn't do is look at absorption kinetics, how fast something's absorbing. Doesn't predict absorption kinetics. It's a single component isotherm or single component test, so it's only looking at one compound. If anybody's looked into detail into PFAS chemistry, it's pretty intense in terms of how PFAS compounds react. I mentioned before my master's degree is in colloids, polymers, and surfaces. One of the first classes I had was talking about forming micelles, and I said to myself, I'm never going to use that again. Well, PFAS compounds at high enough concentration form basically little balls, which are micelles. If you get to a high enough concentration, you can see an increase in absorption capacity on various materials just because of the chemistry of the PFAS compound. And as I mentioned before, isotherms at part per trillion levels are very difficult to work with just because of the amount of material, the volume of water, and the detection limits. So what's the most important thing is how these systems work. Obviously, these are typically pump and treat out of a groundwater. Surface waters can be a gravity filter where the water is flowing down through them. You have water coming in the top. water coming out the bottom, the materials being, the PFAS compounds are being removed in an area what's called the mass transfer zone. The mass transfer zone is basically where the absorption or ion exchange or whatever the process is to remove the compound is taking place. At the top of the bed, you will have what's called spent media, media that cannot remove anymore. And at the bottom of the bed, you'll have basically clean material. As the mass transfer zone moves down through the bed of material, you will have an initial breakthrough time and a saturation point. Well, the initial breakthrough time for PFAS compounds could be either the detection limit or the limit that a governing body has dictated. For instance, in the United States, the EPA has said 4 part per trillion for PFOA, PFOS. So that initial breakthrough time is what's important. The saturation point is basically what's predicted by the adsorption isotherm. The difference between those two is essentially the length of the mass transfer zone. So at the top of the bed where the material is spent is that beginning point of the mass transfer zone. The bottom point where the essentially a fresh material is the end of the mass transfer zone. So why is this important when it comes to PFAS and in particular comparing the various media? As I mentioned before, the isotherm predicts one thing. What we see in the real world is different. These are actual breakthrough curves at 10 and 20 minutes empty bed contact time for granular activated carbon. The influent concentration here was 20 part per trillion, so essentially a drinking water. Run to a 4 part per trillion breakthrough time. If you notice here, the lag bed, excuse me, reaches the 4 part per trillion before the lead bed reaches 13 part per trillion, meaning that the lead bed is not completely saturated. So that adsorption isotherm number that was predicted is not being achieved. You never reach it. The lead bed never reaches saturation. In this case, it's only about 50% saturated before the lag bed has exceeded the EPA limit. The PFAS compounds are different in the way they work in not only carbon, but various media. The mass transfer zone lengths are much longer. So in an activated carbon bed, the mass transfer zone length can be up to 80% of the bed. Whereas a typical compound like trichloroethylene, things like that, the mass transfer zone length is typically in the 25 to 30% of the bed. So very, very long mass transfer zones, very slow adsorption kinetics. In contrast, this is a PureTech G400 breakthrough curve. Again, looking at lead lag here, we're looking at, if you notice, the contact time significantly shorter. So instead of 10 to 20 minutes, here we're operating at 15, 30, and 45 seconds contact time. You also notice that the concentrations are higher in this test that we ran here. So we're running up to 2 part per billion for an inlet concentration. And you can see that there's significant bed volumes of water treated. And here we just picked a point of 20 part per trillion as the breakthrough time. What's interesting to note is if you look at the bed volumes treated at 15, 30, and 45, they each increased by about 20,000 bed volumes, indicating that even at 15,000 or 15-second contact time, the mass transfer zone is being contained. And now, again, this is a relatively clean water. That mass transfer zone length is going to depend on concentration, compounds, and background water quality. But this data here shows this product is highly capable for instance, for point of use, point of entry systems, and more importantly, enabling a very compact system with a long lifespan between changeouts. Some third-party validation. If anybody's familiar with the NSF 4253 conditions, this was testing run at those conditions, so that you have 6 different PFAS compounds in there, and if you notice, the concentrations are relatively high compared to what you'd see, for instance, in a drinking water. But under similar conditions, running to a 20 part per trillion breakthrough, activated carbon lasted about 2,000 bed volumes. I believe we're going to have another webinar at some point on ion exchange, but it's in here in the graph. 9,500 bed volumes, and the PureTech G400 lasted 60,000 bed volumes before reaching the breakthrough point. And again, this is just in relation to an ion exchange resin, which again we'll have more data on later. But just to show, this is a 30-second contact time under those conditions, running to a 4 ppt breakthrough, which is the EPA limits. The PureTech material lasted about 70,000 bed volumes, where the ion exchange resin broke through immediately at 30 seconds contact time. There's significant data been developed. If you notice some of the concentrations here, up to as high as 12 part per billion. and the lifespan of the material is certainly dictated, similar to other products, by the concentration. So we have various contact times and concentrations depending on the compounds and the water quality. But again, low empty bed contact times and measured in seconds rather than in minutes, which again will reduce the system size. So I apologize to the Europeans here because I did this in U.S. units, but I'll make up for it later on when we're talking about some European units. So we'll go both sides of the fence here. But just to compare again to a typical carbon system to a G400 system, minimum contact time on a carbon system is typically 10 minutes for PFAS at a hydraulic loading rate of 2 to 10 GPM per square foot. Excuse me. The PureTech product is as low as 15 seconds. Typically, it's 4 to 16 GPM. Both systems can be backwashed. Typically, there's some pre-filtration, which would be a cartridge filter to remove solids for both systems. But an example of a 100 GPM system, the carbon beds would be a 6-foot diameter. The PureTech would be a 3-foot diameter. The carbon beds would be 6 feet tall. The PureTech system would be about 2 feet tall, and the volume of material is significantly less for the PureTech system. So let's get into the first case study, which actually led to a full-scale application, and this was a site in Sweden that currently is treating AFFF contaminated groundwater. They were using activated carbon that they've been using for years. They trialed our material, the PureTech G400, running at 20 and 40 seconds contact time. So basically 2 beds in series, 20 for the lead, 40 for the total. They're replacing 4,000 liters of activated carbon with 200 liters of G400, and the G400s are operating at an estimate 50% longer time compared to the activated carbon. One of the other important things about this material is it can be destroyed either through incineration or through some destruction processes, which will destroy the absorbed PFAS. So basically breaking the chain, not putting the material into a landfill. Just to give you an idea of the size of these are the tanks that are actually sitting in a laboratory, and you can see if you've ever been in a laboratory, the bench height there in reference to the actual tanks that were being used. And at the site, the big blue tanks in the back were the actual activated carbon tanks, where the ones in the front are the G400 system that was used to replace the activated carbon. Quite a variety of compounds in there. Again, 220-second vessels, influent and effluent concentrations were tested. A lot of different compounds in here. So obviously, for the U.S. folks, it's not something we don't typically look at some of these other ones that are in the water here. Obviously, the Europeans do certainly look at some of these, but basically the PFAS 4 compounds, the top ones there, 100% removal. And if you look at the PFAS 11 compounds, you do see some breakthrough of certain compounds. The PFBA in particular is one. The PFPEA is also one that does breakthrough. But again, very good performance over an extended period of time. So again, just from a graphical standpoint, the essentially 100% removal of the PFAS 4 compounds and varying breakthrough of the PFAS 11. So just some ideas on size of the system. The equipment was about a quarter of the price for the G400 system. It's containerized. It's a small footprint. Those tanks could easily be moved just with a dolly back and forth, rather than having to go on site and to remove all of the media with the truck. It's a lot smaller footprint, and rather than having a truck go out there where you have to pressurize the vessel, slurry the material in and out, here you unscrew the top, unscrew the bottom of the inlet and outlet piping, put a new tank in, hook it back up, and you're gone. So basically, the change out of the equipment can be done in under an hour, probably under 15 minutes, depending on how many vessels you're changing out, compared to typically a day-long process if you're changing out a large carbon unit. Significant reduction in media, so the volume of media is reduced by about 35x. Again, we're changing out the vessel rather than moving the media. And in the disposal, you're significantly reducing the amount of material that needs to be disposed of each year. And obviously, typical disposal costs at an incinerator or some facility are either based on a weight or volume basis. So significant reduction. And logistics, it's a much smaller footprint. Again, these tanks are significantly smaller than you would see with a carbon unit. So what this does in terms of an actual project, rather than looking at the material itself, is how do I reduce the overall cost of ownership? So the rapid kinetics in order to significantly shorter empty bed contact time. From a longevity standpoint, depending on water quality, we can go up to 7x an ion exchange resin, up to 40 times an activated carbon system. Broad range of removal. We have other cases where we're looking at 20 different PFAS compounds. It's a greener material, so 95% reduction in CO2 compared to some of the other materials. And again, smaller installation can definitely do this with reduced equipment size over your standard carbon units. And that leads to it up to a 15% reduction in total cost of ownership compared to legacy products. So just to summarize here, significantly reduced empty bed contact time, again, minutes compared to seconds. Absorption capacity plays a limited role. It's something that, again, if you could use all that capacity, it'd be great, but because of the nature of the PFAS compounds, it doesn't. So it's kinetics play the role. Smaller system size, less waste, easier to exchange, both of which lowers the cost of ownership compared to GAC. And the good thing about it is we're continuing work. So the focus initially on was the PFAS compounds that were certainly of interest to the market, the PFOAs, PFOSs. But there's regulations going certainly with looking at, for instance, the shorter chains and some of the other compounds. So further work is being conducted to further develop the product and improve performance. And I think that's it. So we were open to questions and answers.
Thanks, Neil. I can see some questions here, so I'll just read them out to you and
Yeah.
then you can answer them. So, what is your manufacturing output and do you have product available for shipment?
Yes, we do have product available. We have production capacity on a full scale, so this is not a laboratory produced. The capacity is really going to be dependent on basically what we're seeing in the future in terms of system sizes. But yes, we can get material. We have material that we can do full scale installations.
How is Puretech G400 affected by heavy metals in water?
Um, it depends on which ones they are, but one of the advantages that we have, for instance, is with metals like iron and manganese. You look at some of the other media out there, the iron and manganese has to be removed first. We don't necessarily have that issue, again, because our material can be backwash. So when you backwash it, you're not just disturbing the mass transfer zone of the material. You can backwash the things like that off. But for other metals, one of the first things we do on any application is we'll send out a questionnaire to get an idea of what's in the water and work with our technical folks to make recommendations if we think something needs to be treated prior to the G400.
What flow rates do you operate at?
It's not necessarily a flow rate, it's contact time and linear velocity. So really we could operate it at whatever is out there, but it would fit into our linear velocity and contact time recommendations back on the slide that showed system design.
Can the media be regenerated?
We are working on that. There's currently a project on regeneration. My experience with regeneration in the marketplace right now has, I know there's processes out there for ion exchange and carbon and things, and some of those lead to some logistical problems. But from a chemistry standpoint, we know we can remove the material back off of the product.
Do you sell media or product system or both? How does the media price of G400 compare to GAC?
We sell both. And one of the things we don't talk about necessarily is the price per pound, because obviously it's more expensive than carbon. But again, you look back at taking into account everything, the system size, the disposal costs, that type of information, the overall cost of the life cycle of the project would be reduced if you take into account everything.
What?
One of the things that we will not do, for instance, is drop our material into a typical activated carbon system that's out there right now. Not that it won't work, but from an engineering standpoint, because of our contact time and linear velocity, those large carbon systems are not designed for our media.
What happens to the material after treatment use? Do you take it off-site? How is it disposed of?
I mean, so disposed of by incineration. It could be disposed of by also some of the current destruction technologies. So yes, we would work with the end user on assisting them with an appropriate technology or partner to dispose of the product.
Is there intention to consider applications for drinking water and NSF 61 certification?
Absolutely. Hopefully, we'll have that very soon. We are currently piloting a couple drinking water sites right now, knowing that the NSF certifications is soon to follow here.
What is the cost of the GAC that you took into account in comparison? What was the type of GAC? Do you have any specs you can share?
It would be your typical agglomerated bituminous materials, which are kind of the more or less the gold standard for the activated carbons that are out there in the marketplace for PFAS.
What is the lead time for Puretech G400?
Depending on volume, we have material right now. So, if it's a volume that we currently have in inventory, we can ship that, out relatively quickly. Obviously, if it's a larger system, we would certainly work with you on what those timeframes would be.
Is chlorine affecting the capacity? Is it possible to use the media without backwashing?
It is possible to use it without backwashing for sure. Typically with any granular medium, when you first put it online, you want to backwash it to remove some fines and also to stratify the bed, make the little particles go to the top and the bigger ones go to the bottom. But in theory, you could operate it without. I mean, obviously, it does affect pressure drop as well. In terms of chlorine, data we have to date on typical chlorine levels, we're not seeing an effect. It's a question that does come up because obviously some places are using chloramine and other oxidants, so it's ongoing work. But for typical concentrations we'd see in a water, we don't see a concern.
Is G400 affected by background TOC levels, let's say around 12 milligrams per liter?
We've done some work up to around 10 and not seeing any major impact. Obviously, the biggest challenge with TOC is what is that TOC? If it's large molecular weight TOC compared to small molecular weight, there may be some differences. So what we would recommend, especially at higher TOC concentrations, is probably to do some laboratory work. Either we could get a sample to you or potentially set up a pilot at the site. So we would again work with the end users on evaluating that.
Is there any leaching during application and at what level?
Um, it's the NSF certification. I mean, obviously it would be to pass NSF 61. There's no leaching of anything that's hazardous. That's a concern. But just like every other material, activated carbon, when you first put it online, you have some arsenic leaching. The ion exchange resins, you have some organic leaching. So, we will meet the NSF 61 criteria.
You're looking at removing PPT levels. Would this work removing from ppm to low ppb levels?
We've actually done some work at PPB levels as well. And, in theory, concentration, you can go up to as high as you want with the correct system design. Obviously, the amount of time between media changeouts is going to increase as concentration increases. So in theory, it could operate at ppm. Obviously, there's applications out there now where you're, for instance, rinsing of AFFF equipment, where you may have some ppm levels. In theory, you could operate at those concentrations, but again, your frequency of changeout would be more.
How does G400 compare to Dexorb?
Um, I don't have any side-by-side data. Again, knowing what we know here and knowing the pilot studies, things like that out there, we would operate again significantly shorter contact times than that product.
Can the product be used for highly PFA contaminated material like firefighting water with PFA contamination from PFA firefighting foam?
That gets back to the high concentration question that just came before. And yes, in theory, but again, your frequency of changeout is going to increase.
Can I use PureTech G400 as a drop-in solution for my GAC vessel?
No, and again, it gets back to an engineering. It's not necessarily a performance thing. I mean, if you look at a carbon vessel, typically the bed depth of carbon in there, in a 10-foot, 12-foot vessel, maybe 6 to 8 feet. Our vessel here, because of the flow rates, the linear velocities and contact times, you'd end up with a very, very thin layer of our material if you put it in there. And again, flow distribution could be an issue.
What kind of pressure drop do you see from your medium?
Be similar to any other 20 by 50 product. We would supply the technical data sheet and all that information's on there.
So those are actually all the questions. We can wait for a few more to come through if anyone else wants to ask a question.
And if you notice on the Q&A page, there's an email address if you have any other questions. I know many of you have my contact information, and although I did told Addie before, we'll just let it go to the standard email. If you want to email me directly, it's just Neal@puraffinity.com, Neal. So you could feel free to email that if something pops up in an hour from now and you wanted to ask.
We have got one more question. What markets are you currently operating in?
Yes. All of them. Yeah, anywhere. I mean, obviously, the point of use, point of entry, municipal ones require the NSF certification, which again we're actively working on right now. But we're doing pilots anywhere from drinking water up to landfill leachate. So across the board and varying water qualities.
And if you load your GSE with aluminum or iron, would you expect similar absorption results to what you get with the Puretech G400 compound?
Um, that's a tough question. I mean, from an iron standpoint, there's some possibilities, depending on pH, depending on concentration, that type of thing, where you could coat the material and basically essentially cover up the pore structure and cause some problems. And I've seen carbons over the years where you pull them out and they're orange. So that can certainly cause a problem, but it's really water quality dependent.
Are you willing to share your slides?
Feel free to email us. This is obviously a public forum, so anything in here that is in fact, I know there's nothing in here that's confidential.
Yeah. And then maybe we can end on this one. What level of interest is PureTech G400 currently generating?
It's generating quite a bit of interest. I mean, I came on board in January. And I think this application in general is causing the market to to look at things a little differently. I mean, if you think about regulations in various compounds, typically things have been in the ppm range. I know, again, being in the industry for 35 years, when things went to the ppb range, we all went, whoa, now we're ppt. It's a different thing. You have people that have been using, for instance, activated carbon to remove other compounds in the water, chlorinated solvents that the carbon's lasting a year, and now all of a sudden they're getting PFAS at PPT levels, and in theory may have to change the carbon out in 3 to 4 months. It's certainly making the industry look at some things and figure out what's the best way to solve them.
So thank you so much, Neil, for that. And thank you to everyone who joined. We hope you found this session valuable and insightful. Just a quick few reminders. The session will be recorded and we will share that in the coming days. We'll also share along additional materials. And if you have any interest to see how PureTech can help you with your projects, feel free to reach out to the email on the screen and follow us on LinkedIn if you haven't already. And for any updates regarding Puraffinity, keep up to date with our website as well. Wish you all a good day and thanks again for joining.